Okay, this is our second problem for simple harmonic oscillators using ladder operators. Here's another one that there isn't really a nice way to put it. You might be very tempted to kind of just use like math magic on. Not gonna recommend that, because not only is your grader gonna notice, it's gonna make them mad. Like, it's just annoying. Like, it kind of sends the message that either you don't think your grader is actually reading your solutions, or you don't think the grader understands the solutions himself. So, not saying that's the case, just having been in that position, when you're already kind of overworked and in a bad mood, that doesn't help. So take a little bit of mercy on your grader and, try to at least show the spirit of the solution. Especially when the grader has to do their own solutions. Yeah, it can really get a little bit annoying when you spent like an hour making a solution to a problem, and clearly people in the class are spending less time working it out. Like I said, it's not a big deal, but it's one of those little things that helps karma, possibly your grade. So just beware with this one, because the whole point here is to show this, not to take it for granted, especially this part. And you could tell I did this one right before doing the last video because I was trying to get this solution instead of what the other one was asking for. So our point here is we want to show that the raising and lowering operators are generating new solutions to the Schrödinger equation, meaning that we can't normalize, say, ground state wave function and have that same normalization constant be valid for all the energy levels, because it's not. But each one is normalized. So, if psi n is a solution, it is normalizable. So is the next energy state up. That is also normalizable. Or the next energy state down, with the exception of n equal to 0, which we showed in the last problem. So these are all valid. But if we normalize this, this is not normalized. Each one has to be normalized. So, I guess for example, if we looked at equation 2.50, where we have our psi n, it equals some normalization constant a n, and then the ladder operator applied n number of times, and then our ground state wave function looks like this. If we had psi n plus 1, we have a different normalization constant. And then we have n plus 1 acting on this. So the normalization constant is different. So what we're going to do is do the same method we did in the last problem. So hopefully once you saw it in the last problem, I know it's not super obvious to just look at it and know exactly what he did. It takes a while to figure it out. Don't worry about that. And don't feel bad if you do. It took me, this part after I did the first problem was pretty easy because it's the same exact technique. This one took a while. I just ended up going to bed. Went to bed, woke up this morning, figured it out. So if you're at that state, go to bed, wake up, do it the next day. I know it's hard to let stuff go, but that'll help you out. I'm pointing this out not to say that I'm dumb. I'm pointing it out to say that everybody's dumb. I know you're probably in class with a bunch of people that are saying the homework's super duper easy and they never have to try. I had somebody in my grad school quantum mechanics class say that he just literally sat in the back and played video games the entire class and still got an A. It's so stupid why I'm in this class. Yeah, those people are jackasses. And if you are one of those people, I'm not apologizing for calling you a jackass. So let's go ahead and get into it. We're going to start with the raising operator. So my goal here, because this is like the problem, is to show that this is the case. In order to show that it's the case, that does not mean that I just declare that the raising operator and the lowering operator are Hermitian conjugates of each other. That's not the point of the problem. The problem is to show explicitly that this equation is valid. That we can use as our argument later to show that they are Hermitian conjugates of each other. We can't use the end of the argument to justify the beginning of the argument. That's circular reasoning. We have to do this step first before we go into proving that they are Hermitian conjugates of each other. So this guy here, so we have our raising operator acting on psi n, and we know that that is a normalizable solution. It is not going to be equal to 1, even though we know that this is equal to 1 squared. This first integral is not equal to 1 because our normalization constants are not the same for each energy state. What we're going to try to do is solve for what factor these two differ by. So we want to solve for the factor that they differ by. That's the heart of this problem. That's what we're trying to show with this. We want to see how the raising operator is related to the wave function in the raised energy state. Not be all hand wavy about it. So we're going to be doing our same integration by parts trick that we did in the last one. And yeah, I'm going to show it all explicitly because that's the point of the problem. So we have our complex conjugate times this guy. Now I am going to just write this one out. So this is what our ladder operators look like. I also have zero sense of pride about memorization. I mean, no, I don't think like you should never learn anything because you can look it up all up on Google, but people write books for a reason. You write stuff down for a reason. Okay, so now that I have my ladder operator, I am going to go ahead and have that A plus operator act on the psi n. So now I have h bar over I acting on the complex conjugate. And then that was our raising operator. But remember, we are going to be taking the complex conjugate, right? So we have the complex conjugate of our psi n, but we also have our complex conjugate of our raising operator, meaning that this plus sign became a negative sign, and so did the first one. So The raising and lowering operators are not simple complex conjugates of each other. Yeah, they are Hermitian conjugates, but they're not a simple complex conjugate, because you got that. Both parts of it are complex. And no, it's not a typo in Griffiths, by the way. Heard that one too. I think if you're thinking that, I think the issue is there's a slightly different formulation. That is a creation and annihilation operator. Is probably what you're thinking of there. So I'm going to go ahead and pull through the A plus psi naught, and we're going to go ahead and let's just break it into two integrals now. So there is another way to formulate it with creation and annihilation operators. That's not what we're doing right now. I can't remember if Griffiths gets there or not. Probably Griffiths does, but I honestly don't remember. It might have just been in Landau. Oh. And you know what? I wanted to go ahead and break it apart into two integrals. So let's go ahead and do that, because that makes my integration by parts more explicit. So I'm just going to integrate the first one by parts. Feel free to take the constants out if you want to. I'm going to just keep them in. So you could just multiply everything by the constants. I'm just going to roll them all up into my v term, just cuz. So that's going to be my u, and I'm going to say that that's my dv. Because it's far too easy to make a sign mistake. For me, at least. So then my du is just dx. Raising operator acted on psi n. My v is just the integral of that. So let's go ahead and write the dv first. So that's going to be negative 1 over 2m. And then we have h bar over I. And then we have d psi complex conjugate dx. And then if we integrate that, we of course get the same constants out in front. And then I just get psi n. Integration of parts looks like this. So we have u dv equals uv evaluated at the limits minus v du. So now this is going to equal our u. I think I'll just throw these constants out in front. So we'll do v and u. My operator has a function to act on, so I can be a little loose with the order there. That's evaluated at positive infinity and negative infinity. Now I have negative integral dx of v, and you'll notice I had a negative sign in my v, so it would not behoove you to just pretend like magic happened there. And then that's psi n complex conjugate, and then du is just dx of ladder operator acting on psi function n. And then my second integral I'm just going to pull down because I didn't really do anything to it. Now the first one, where we have them evaluated, we're using equation 2.50 again. So psi n is normalization constant times ladder operator applied n number of times to the ground state wave function. Now if I evaluate that as x goes to positive or negative infinity, what I get is e to the negative infinity, which is 0. So e to negative infinity is 0, e to positive infinity is 0. Well, I have e to negative infinity squared, so that makes it to negative infinity. E to positive infinity squared, e to the negative positive infinity squared makes it to negative infinity. So I get 0 no matter what, which is good for us because that ended up working out. Now here, what is now my first integral, I get a positive sign because I had that negative sign out in front before. And I'm going to roll these two integrals into one again. So they are both times square root 1 over square root 2m. My first one, I have h bar over I, complex conjugate psi n, d dx a plus psi n. And now we have minus I m omega x, complex conjugate psi n, and then ladder operator acting on psi n. Okay, now we can go ahead and pull out that psi n because we don't have any derivative acting on it. That complex conjugate psi n, I have 1 over square root 2m, and then I get h bar over I d dx. I'm going to pull these guys out here, minus I m omega x, and then that's all acting on raising operator on the wave function. This is now my lowering operator. So what I have here is complex conjugate of the wave function times lowering operator, raising operator, psi n. Now we're going to use equation, I think it's 2.46, which we spent a lot of time in that section getting. Oh, actually, I think this is 2.43, one of those. Let's take a look. 2.43. So then if I go ahead and solve that for a minus a plus psi n, I get en psi n plus 1/2 h bar omega. We can go ahead and put that in here. So that's going to be En plus 1/2 h bar omega, psi n. We can go ahead and factor that out. So I have En plus h bar omega, and then I have complex conjugate psi times psi n. Now I'm going to use equation 2.50 again, where I know that En is n plus 1/2 h bar omega, or that's in h bar omega plus 1/2 h bar omega. So that means that I have in h bar omega plus 1/2 h bar omega plus 1/2 h bar omega, and then times the integral of my wave function squared, the absolute value of my wave function squared, which is 1. So there's our answer right there for the first part. We showed that if we did the raising operator times psi n, absolute value of that squared, that equals in h bar plus 1/2 h bar omega plus 1/2 h bar omega. So that's n plus 1 h bar omega. Now we're not quite done yet. Because what we want here, just going to pull up part A, we want to find out how these scale. We're close though. So now we have this guy. Let's just say what our result was. So I know this now. So I showed this first part. Now I need to take this and show this part. So, like I said before, I know that each step is normalizable, right? So I want to see how these guys scale. So I know that this equals 1, right? I also know that this guy equals 1 because it's normalizable too. But I want to see how these constants scale. So let's start with this guy. So I know that this has a normalizable solution. I know that's equal to 1. I'm going to use equation 2.50 again. That's where I know that my psi n is an, raising operator applied in number of times. So now I'm just going to replace that in here. So I have n plus 1, so that's n plus 1. Raising operator applied n plus 1 times. And then times my ground state wave function. And I know all of that equals 1. Now, I'm just going to simplify this in a very, very simple way. And that's knowing that this raising operator applied n plus 1 times. I could also write like this. Now, A, by capital A, normalization constant, n plus 1, is a constant. I kind of gave that one away. So this operator that takes a derivative with respect to x, it doesn't matter what order I put the operator and the constant in. So I'm just going to rearrange it. So now I'm going to put that, I'm just going to pull this guy out because it's a constant. I suppose I should put it in absolute values, but I guess I'm good. And I'm just going to have this. All of that equals 1. Now I want to recover a psi n, because I know what the integral of ladder operator acting on psi n, absolute value squared, equals. So I would like to get that into here. So what I'm going to do is I am going to multiply both sides by an squared. And now to kind of to follow Griffiths' lead here, to keep the wave functions real, I'm going to multiply it by negative. Now I'm going to pass that guy into here in between these operators, because the operators aren't acting on it. So now I have the absolute value. Since I have the absolute value, it doesn't matter that I called it a negative number, because I'm only taking the absolute value anyway. Oh, whoops. And then it is going to be inside that squared. And then that's a plus to the n. And then that whole guy. And then that equals negative an squared. Now this is psi n. So let's go ahead and call that psi n. So I have raising operator acting on psi n squared equals negative an squared. I know what that integral equals because I spent all this time doing it just now. So that equals n plus 1 h bar omega equals an squared. Or what I have at this point is I have I think I'll put the other one first. So I take the square root of both sides, negative, so, and that's just to keep the wave function real, no other reason for that. Completely arbitrary. There we go, an. So we're getting close to showing this relationship. So what I want to do now is I'd like to get, let's go ahead and just write this down, what we're trying to get, so we can see it. So I want this basically in terms of psi n's. That's what my goal is here. So I want to see how my psi n is affected by a constant if I apply this ladder operator to it. So what I'm going to do is I'm going to just multiply both sides by my ladder operator raised to the n plus 1 power, and then that ground state wave function. Whatever I do to one side, I have to do the other side. I'm going to go ahead and, well, we'll just do it this way. But we're going to do that same idea where we're going to break apart that ladder operator to the n plus 1 power and put 1 on the other side. So this one here, this just flat out is psi n plus 1. Now I'm going to break apart the operator powers. So I have a plus, a plus raised to the n, raised to this whole ground state wave function. And what I get is this really nice scaling factor. Oops. Which tells me, because this is just psi n, that if I apply a raising operator to psi n, I get I times the square root of n plus 1 h bar omega all under the square root times the next highest energy level wave function. That's 1. So we did half of A. Now let's go ahead and start tackling the other half of A, which hopefully still got to show it because that's the problem. But here's where you can, at least justify being a little bit less explicit with each step, because you already showed it once and it's the exact same method. Again, just saying, ergo, you could do the same thing with the lowering operator. If you want to risk putting your grader in a pissy mood, go ahead. But that's going to be the result. So people who grade these are human too. So we're going to go ahead and show it because that's, what you do. That's what the problem is. And plus it's, if you're not interested in showing it and actually interested in how this nice result comes out, then, maybe this isn't a good class for you. Maybe you have to take it. Maybe you're an astronomer. I'm going to go ahead and pass in complex conjugate a psi and A minus psi n at the same time. I said here it's okay to take some liberties when you've done it once already. Okay, now this one is the complex conjugate of A minus, so that makes that a plus sign, and then we have a negative sign there. Now I'm just going to go ahead and break that into two integrals. That is A minus. This is the exact same one we did in the first one. And then that's a plus. Or not the first, I meant the previous problem. This is the exact same one that we did in problem 2.11. And then that's I m omega x, complex conjugate, lowering operator acting on psi. We're going to do integration by parts. So my u is going to be this, making my du the x derivative. My v, I'm going to keep the constants in there. My dv, I'm going to keep the constants in there. So it's 1 over square root 2m negative h bar over I spatial derivative of the wave function complex conjugate. So then my v, the integration of that is very easy because all I have to do is, just apply the fundamental rule of calculus. Okay, now we're going to go ahead and take v and u. So I get this guy and this guy evaluated plus negative and positive infinity minus dx, and now we want v. So v does have a negative sign there. And that's going to be times complex conjugate. And then du is ddx of this guy. And now we're going to take our second integral and just pull it down because we didn't care about it. That's really the trick of this problem and the previous one, was knowing where you're supposed to apply the integration by parts. Once you apply it to the first one, it kind of comes together. Now this goes to 0, which we already justified. And then we have minus, minus, so we get a positive, and we're going to throw those integrals together. So my first term is now positive. My second term is also positive. And we can pull out the size to go out in front. And then these are going to go back here because the operator is acting on them. So what I have is the integral equals complex conjugate, raising operator, because that has positive and positive, so that's the raising operator, times the lowering operator, times psi n. Now we're going to use that equation. I believe this one was 2.46, and we are going to replace the a plus a minus acting on psi n with energy En times psi n minus 1/2 h bar omega psi n. Let's just go ahead and pull this up so we remember what we're doing. So I'm going to go ahead and replace that in there. So now I have psi complex conjugate E minus 1/2 h bar omega psi n. And then I'm going to use the equation 2.50, which is this. Oops. And I'm going to pull that out in front. So I have n h bar omega plus 1/2 h bar omega, that's my En, minus 1/2 h bar omega, and then times the integral of the absolute value of psi n squared, which we know that's normalizable, so that is 1. These guys cancel out. So my final result, well, not quite final. This result we have and that's that it equals in h bar omega. Okay, again, we know that clearly because we already used it. We know that this equals to 1. We also know that the lower energy state equals to 1. We want to find out what the scaling factor is between those two constants, between capital A n and capital A n minus 1. So we have psi in would be capital A-N. This guy. And then we have n minus 1. Now this one I do want to point something out. So this doesn't get hand wavy here. So if I have n minus 1, then that's the same as going up in steps. So you go up in steps and then go down 1. So that's the same as going up in steps and going down 1. That's the lowering operator. Our order isn't going to matter for that, so I can go ahead and write that this way. So I could either go up in number of steps and down 1, or I could go down 1 step and then up in steps, and that'll still get me the same number of steps. So I did want to take a second to point that out before we go on. So what we're going to start with is this solution, because we know that this is a normalizable solution. N does not equal 0. Now let's write out what that is explicitly, because that's the point. So now we have squared. Now we have a capital A n minus 1, and then I'm going to have go down 1 step, go up in steps, and m omega x squared. Now I'm going to do the same thing I did before. I'm going to multiply both sides by an, and I'm going to multiply it just by the negative because I want the wave function to be real. So, because we're going with this assumption this guy's real. If we don't put in that I, then we get into a little bit of trouble with the way this all works out. So we're just avoiding that trouble right now. So and I'm going to pull out the n minus 1 squared because that's a constant. I have my lowering operator. I have my an, because now I passed it into the absolute values. Now this is just psi n. So what I have is a to the n minus 1, and then I have my integral dx of my lowering operator acting on psi n squared equals this. And then I know what that equals because we just worked that out. At least I know what the integral equals. That equals n h bar omega. Now I take the square root of both sides, and what I get, I'm going to come up here, is I n h bar omega square root a to the n minus 1 equals a n. Now we're going to do our same thing. We're going to put in what the size are. So I'm going to multiply both sides by ladder operator to the n minus 1 times, and then this, and then we're going to have a n, and I'm going to say down 1 step, up n steps is the same thing because it is. And then I can move this guy to the other side, and what I get is I times the square root of n h bar omega psi n minus 1 equals lowering operator acting on psi n. So we got both of those. So for part A, what we showed was the scaling factor between those raising up a state and going down a state. So for A, so we showed explicitly a n psi n plus 1. That one is n plus 1 under the square root. And then psi, psi n plus 1. So we showed the scaling factor if we apply a raising operator, and we also showed the scaling factor if we apply a lowering operator. So in short, the normalization constants, they're not the same. So we do not have an equal probability to find our particle in any energy state. That's kind of the gist of that. There is not an equal probability to find our particle in different energy states, which isn't too shocking. I mean, that's we've seen that before. That's been true of an infinite square well too. Okay, now let's go into part B. Let's just go ahead and take a new page, and we'll go into part B so we can pull it up. Let's just pull up what part B is. So now we want to use equation 2.52. By the way, equation 2.52 was just that result that we showed this guy. To find out what AN is. So we want to discover what AN is using that equation. Now the nice thing about actually working it all out by hand, you're kind of supposed to, is that we can go ahead and put this in a more useful state, which was our intermediate solution, which was where we had I square root n plus 1 h bar, what we got right after the integral, a n plus 1 equals a n, because what we care about is a n here. So this is more useful form. And we know it right away, because we solved it explicitly. If you didn't get this intermediate state when you were trying to solve the other one explicitly, you've got more problems than I can maybe help you with. Okay, so we want to know where to start though. So the easiest place to start is always let's start with n equals 0. Let's start with ground state, because ground state's easy, right? So I have a relationship where if I know what A of a specific energy level is, I can find the next energy level up. So I would like to find the bottom rung of my energy ladder. So I'm going to find the bottom rung first. So my bottom rung is going to be this psi naught. And we know that's going to be A naught. And then you have your ladder operator raised to the 0 power. And then times this guy. So there is no ladder operator there. So now I'm going to go ahead and integrate that over all space. I know that that equals 1 because it's normalized, because I'm going to make it normalized. Now I have A naught times this guy squared. You'll notice my wave function is real. That was one thing that I wanted to make sure I preserved. And then we just have this e to the negative m omega x squared over h bar. All that equals 1. Now I'm going to go ahead and do u substitution. So I'm going to say that u is the square root of m omega h bar times x. X is not under the square root. And then if I have du dx, that just equals that's m omega h bar. So my dx is h bar, square root of h bar over m omega times du. I'm going to go ahead and substitute that in. So that gives me we'll throw the constant outside the integral. That gives me this constant factor. My integral from 0 to negative infinity to positive infinity, because that, like if I plugged in x equals negative infinity, u is negative infinity. If I plugged in x is equal to positive infinity, that u is positive infinity. Then I have du minus e to the negative u squared. If you want, you can always look that up on an integral table. I have it right here. So e to the negative x squared dx is just square root of pi. So what I get is a naught squared h bar pi over m omega, and all of that equals 1. So that means that my a naught is equal to m omega over h bar pi to the 1/4 power. So now I have my bottom rung normalization constant. So I am able to normalize the bottom rung. Now I can use my useful formula here. A(n) equals I n plus 1 h bar omega n plus 1. So I'm going to rearrange this just a little bit. I'm going to solve it for a n plus 1. So then I get 1 over, and then I have I n plus 1 h bar omega. times an. I'm going to clean that up just a tad, just because it gets confusing. So I'm just going to put a negative I on top. That's just to help out. N plus 1, and then that's an. So now let's plug in n equals 0. I'll plug it in over here so it's a little bit more separated. Alright, n equals 0 gives me a 1 negative I over 0 plus 1 h bar omega a naught. So that gives me, let's just go ahead and replace a naught here with m omega over h bar pi to the 1/4 power. Okay, now let's plug in n equals 1. So that gives me a2. That'll be negative I over n, not n. We're going to have n equals 1. 1 plus 1 h bar omega, and now this would have to be times a1. So that's times negative I over 0 plus 1 h bar omega, and then this guy. And I could keep going, but I want to find the pattern to get a to the n, and I think I have enough to find that pattern here. I apologize, I'm going to, like, this kind of two different n's. This used to confuse me a lot, so I used to just like change the subscript to k. But we'll keep it as just n. So if I have a to the n, like here, I have a to the 2, I have negative I times negative I, so I have negative I 2 times. So that gives me a negative I to the n power. So this is now my n. Then on the bottom I have a square root. I have h bar omega, I have 2 times. If I look at a1, I just had 1 h bar omega. So that's h bar omega to the n power. And then of course I have this guy. This guy just stays the same. Then here I have 0 plus 1, and then 1 plus 1. So if I have n equals 2, I have n times n minus 1. If I went on to do an A3, this might be a little bit more clear. I would have, now I would have 2 plus 1 h bar omega, and then times this, which would be 1 plus 1 h bar omega, because now I have to times it by a2. And then we had the 0 plus 1 h bar omega, and then we had this guy out here. So that gives me 3 times 2 times 1, or 3 factorial. If it's a to the 3, this gives me 1 times 2, 2 factorial, 1. So I have n factorial. And there we go. This is my general formula. I have a to the n is negative I to the n power over the square root of n factorial times h bar omega to the n power times a naught, which was m omega h bar pi to the 1/4. And And with that, I can calculate all of my A's. And he gave us our answer right here. So that matches. We're all happy. And now we can find our normalization constant. And we can find out, that it changes by this factor here times each A naught. So every time we go up in energy level, we don't just our normalization constant isn't evenly spaced. It's going to depend here. The bigger, you'll see the is going to fluctuate between being real and being imaginary. And you're also going to see that the bigger n gets, so as n gets bigger and bigger, our normalization constant gets smaller and smaller. So this is a pattern that we saw in the infinite square well too. Higher level energy states are less probable than lower level energy states. This is also what we expect from classical mechanics. Things are going to relax into low energy states. Nature's lazy. Turns out we get it from somewhere. So, just as you have a ball on a hill, classically, we know that's just going to fall down to the bottom. In quantum mechanics, we have a probability that it's just going to stick there. But the probability of finding it in the ground state is much higher. And there you go. That's problem 2.12. A double asterisk problem. That's probably why it took an hour.